Okay, I think that's actually fine. Other than maybe I turn this down a little bit. And then also, I want to test, I want to see if it sounds okay. So, because I was messing around on my laptop, I think before, my audio has kind of gotten a little bit disconnected. My screen also was just recording all black. Today, what I want to do is go through Hecke.jl again and start developing for the Hecke/Oscar ecosystem, the Computer Algebra Systems project. And so that's my goal. Just trying to get everything in place. I'm not sure why my... Yeah, I'm not sure why anything is working the way that it is, but I think it's fine. So let's try just pulling up a browser, going to YouTube, and then I'm going to probably mute this for a second. We're getting there. This is hella loud now. And this is still a little bit loud. That's still a little bit loud. Okay. So I think we should be good now. Good to go. So what is there to do for Hecke.jl? Well, last time, let me just keep you up to date. Last time we implemented a central simple algebra type. So now there's associative algebras, there's also central simple algebras, and crucially things that we need to do are we need to implement some further types. So the type of like a matrix algebra. It's currently available inside of the associative algebras in Hecke. And we're just gonna essentially duplicate that, I think, is what I was thinking for central simple algebras. So we'll call them maybe split algebras. Afterwards, there's like things that we could do, like implement simple algebras, but more importantly, we need to find out a way to, for example, compute the reduced trace and norm or reduced characteristic polynomial from like a bare bones algebra. Another thing that I thought was when you have two central simple algebras, you want to tensor them often. And so we should implement some tensor product structure inside the associative algebras functionality. That way we can tensor product two associative algebras get another associative algebra, and when this tensor product interacts on two central simple algebras, it should obviously put back another central simple algebra. And what that means is that we need some abstract type that captures the concept of a central simple algebra in terms of like structure constants. So that's kind of the goal. So let's try just going back to this package and pulling up where we left off. So there were also some smaller things that I forgot to do. Namely, when you do exponentiation inside of a central simple algebra, there's a limit on the size of exponents that you can have, and that shouldn't be true. Not that anyone's going to care about exponentiating a central simple algebra to some elements like the 2 to the 130th power, but you should be allowed to do that and throw an error. I feel like there's something saying that my internet is bad right now, but that's just like, seems like it couldn't be true. Yeah. We're gonna ignore that, yeah. Maybe it went down for a second, but... So, we could start making some lists in here. So, for example, let's do, how do I think if I open up one of these, like with S or something, splits, nice. So, what I wanted to do was essentially copy this. And now we can quit. going to put that there. So this is going to be quaternion algebras. And then the way that we're going to get this list is essentially by putting it in place. So what else do we need? We'll need split algebras. And actually this should probably be up top, is what I would argue. God, I've got to like look at my keyboard, although I know I don't need to. Just for the confidence. Okay, so split algebras, quaternion algebras. What else should we use? There's going to be one for symbol algebras. That might be the next one. We'll have cross product algebras. And there's one other type, which is probably something that should go up to basically the top, which is like an abstract type. It's either going to be top or bottom. I think it'll be bottom. It'll just go in like increasing generality. So the last version that we need is last version that we need at the moment. It's like, because we could also instate like a cyclic algebra. We have like a cyclic extension, and then you define the algebra just based off of this cyclic extension and then one other element inside the base field. I would call these generic algebras, but the way that this kind of system is calling things, I think you'd call this something like structure constant central sum algebras. I mean something from like structure constants. I would call it abstract, but that's not a good way to do it. Maybe just general. So structure constant central symbol algebra is just going to be a central symbol algebra that's defined by a multiplication table. And I think there's not much else that you can really call from that. When you have two algebras and you tensor product them, you're probably going to get a structure constant central symbol algebra again. There's one exception to this, which is like biquaternion algebras. So I know this is ridiculous, but we're also going to have a biquaternion algebra. Type, and I want that just so that we can call easily certain functionality for like quadratic forms. So biquaternion algebras have a canonical involution, and that involution is related to a quadratic form that you can get from the algebras. So I think these are the main types that we're going to be working with. Yeah. So let's try going to the top here and copying some of this stuff. So, for example, this I'm going to copy because this is going to be the foundation for our general structure. Constant algebra, central simple algebra. Actually. And then there's like simple things that we can change right now, so. So I think this will be central simple structure constant algebras. I know that's a long type. CSA. And it's going to be an abstract central simple algebra. So is it simple? It needs to be yes. And semi-simple, some of these things we'll fix. The thing is, we're gonna have to replace, fuck. What did I just do? Yeah, undo that. What was the last thing that I undid? Redo that. So instead of structure constant algebra, we're going to replace this with central simple. Structure constant algebra. And obviously the one that was already there needs to go away. I'm kind of gonna, I think, put this here like this. For now, basis. It's an associative algebra LM, central simple structure constant algebra. There's also gens. So let's find Matt. Ouch. Actually, I want this. And we're going to... We're gonna copy all of this, because I'm not looking at it right now. I know that some of them, though, are not necessarily needed. So... let's put that there. And... okay. So the type also is going to be of type, it's going to be a split algebra. That's what we're going to call it. And some of these things aren't needed, right? So coefficient ring, not necessarily needed. So S, I think, also is not necessarily needed. Coefficient ring is like, at least the way that it's defined in the associative algebras package, it's like you have a matrix over S. So it's like the matrix ring of n by n matrices with coefficients in S, and then you consider that as an algebra over the base ring. For us, there's a little bit of a choice whether we want to have like split algebras, tensor, another algebra being kind of like a matrix algebra over something, or if we want to just call that as another central symbol algebra. And I think there's probably some optimization there. Like I imagine that matrix operations with coefficient rings probably a little bit faster than if we ported everything into a structure constant algebra and then tried doing kind of like sparse multiplication. Not that I expect anyone to necessarily use these objects for actually computing like algebra with the elements. But we'll try to figure that out. So one thing that I do need to do though is just go run and get my laundry. So it was in the dryer. And I think I'll do that and then I'll just be right back. Okay. So, I think if we make a type split algebra, there's really like no point in. I mean, there's some amount of point in trying to make it so that operations are still fast, but like, yeah, if it presents a problem in the future, I'll fix it. Undo. So I think I could just do that. Right, okay. We'll get rid of this. Undo. Dimension is an int, degree is square root is dimension. Is simple should be a yes. I think there's a 1 in here. So because we're gonna call it from they should all be simple. Yeah. So I think we'd have to specify that to some extent. But it is of type abstract central symbol algebra, so it's more like S was a coefficient vector, right? So what does this call to 1 mean? So S is a dense matrix type of the coefficient ring. Is a dense matrix type of the coefficient ring. And it's S is a dense matrix type coefficient ring. Try to see where this is called. So in this struct, we have matrix algebra elements. And fuck. This is a different type too, so I was just listing algebra types. So maybe we either have to do something like algebras, then elements, or each algebra type has its own LM type. Matrix algebras and like quaternion algebras, you can maybe kind of believe that those are going to be different. Here, having a separate mat algebra LM type. Cross product algebra is probably also going to have a different type for elements. So I think that we should keep these in some sense in their individual types, but then you'd think that if you call a quaternion algebra, the type of the element should be like quaternion algebra element type. In the original implementation, the type was what? It was just associative algebra element. Okay. So I kind of want to reorganize this. So the reason why these are grouped together is because they have elements of the same kind of type. So we could do something like structure constants and symbol algebras. All in the same area, I guess. Okay. I think I got a little bit carried away in some of this. So quaternion algebras, let's see what they actually rely on. So we've got a base ring, multiplication table, 1, 0, standard, which is a tuple of type TT. I wonder what that actually calls. So I haven't written anything yet, which means that I think I can do just using Hecke. And we can call quaternion algebra -1, -1. And I wonder if it just prints -1, -1. So what about quaternion algebra GF2 0, 1 0, 1? Okay. I wonder if that is because it prints a tuple, right? That's why it's got parentheses. I was kind of wondering if I could make it print something like this instead. Not that it's important. Biquaternion algebras I can see being a little bit weird in the sense that you don't ever really want to define a biquaternion algebra, although you could. Kind of the way that I would imagine people would define a biquaternion algebra is you define two quaternion algebras and then you tensor them together. But there is going to be, I think, functionality for checking exponents of algebras at some point. And in that case, if you check an algebra and it's got like degree 4 and exponent 2, then I think there should be some function which makes it a biquaternion algebra. And you could probably call to get two quaternion algebras that tensor to give you the algebra that you started with. Could see that being true. So let's leave this open, actually, see if we maybe need it in the future. And start trying to reorganize some of this. So I think this one is not so important. For us, it's going to be of type T. So we could probably just like leave that there. Center. I don't think this really matters. Because our center is going to be our base ring. Is simple should be true. These things should all be also defined over fields. But I don't think I'm gonna insist on that to some extent. Okay, so how do we define a new one of these? We're gonna just call split algebra on T with a ring. That's gonna give us a new one. Great. Probably some more of this we could fill out. So it is simple. All of these are like 0 is don't know. Number 1 is true. Number 2 is known and false. I hate to say that kind of shouldn't be true, but put that in whenever. So here, I think this just defines standard multiplication. Canonical basis is an int, whether or not we take a j minus 1 times n plus I to be eij, or where eij is e sub kl sub kl. It's kind of interesting to me that this is even a thing. So let's do like A is mat algebra of QQ. What else do I need to call here? Okay, and now let's see what a dot canonical basis is. 1. And if I call a like 1, that actually prints something. I'll tell you right now, that was unexpected to me. It went like that. So it goes down the columns before it moves over a row. Which I would expect it to move over a row before moving down a column. But that's okay. Q if I call like this. I'm actually surprised. I have no idea what that means. Like, it calls. I mean, yeah, I have no idea why that would be. So Q is just a quaternion algebra, right? And when you call these like Q1, Q2, Q3, Q4, we're getting back basis vectors. And so how do I think about this as being a call to a list? So this is obviously just telling me some well, I don't know if it's obvious. It's not even really clear to me. Like if I just did it's get index, right? Yeah, I want to know. It's like Q5 doesn't print anything, right? I wonder where this get index function is located. Okay, I don't know what the... It's an LM. Okay, so the function calls just the ith basis element. Cool. Didn't know that. Did I really input something here? On accident. So this kind of thing I think we can just get rid of. Because why would we call matrix algebra with another coefficient ring other than, you know, for a canonical way to think about elements of the tensor product. Okay, I'm just gonna delete it. Matrix algebra LM. So this is gonna be split algebra LM. S is a matrix element. We're no longer gonna use that. Parent. It's gonna be split algebra. Over the coefficient ring of the parent. Fuck. So kind of don't think that we need this, but I know I'm gonna fuck this up in some sense. Has coefficients is weird. God. I feel like I'm gonna fuck a bunch of stuff up because I don't know what basically the reason for any of these things is. So I kind of was just assuming that like when you have a matrix algebra element, it's supposed to be a matrix over an element of like S. And so the type of the coefficients in the matrix would have been S. Or, because it said that matrix should be of type S. So, and S was the coefficient ring. So I can't tell you why that would. I can't tell you why that would be there. At least not obviously to me. I guess we can test first. So let's try doing like let's do like Q is quaternion algebra, and then let's try doing so what's the call? What would the call be for matrix algebra over quaternion algebra? How we'd call it is so we just do something like this. So we'll say like MQ. This is going to be, we'll just define it like this. I don't know if that will be a proper call out in Julia. Okay, but this is going to be a matrix algebra over QQ with Q size 2. So let's do dump on this. Basis matrix undefined. Da, 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 da. That is just a crazy amount of stuff. Mostly because the multiplication table, I guess. Coefficient ring is quaternion algebra, base rings rational field. How do you call, let's say, basis of M2Q? So the basis, it's presented, that's kind of interesting too. 16 element basis over Q. Great. So 1, 2, oh, okay. I was looking at these as 2 by 2 matrices, but it's right. It's 1, 2, 3, and then 4, and then 1, 2 going down the column and going over 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So let's do element C is going to be basis element, let's say 5. And then see what happens if we dump this. Sorry. So I want to find out. I mean, there's like too much in here to actually like human read it. So let's just start calling stuff on this. So x dot parent, that would make sense. Okay. Let's do x dot matrix. So the matrix was just supposed to print out the matrix presentation of of this thing, but it was listed as type S, so I don't necessarily get that. This is an abstract algebra generic mat space LM of Hecke dot central simple algebra LM QQ field LM. This is a mat space element of type central simple algebra LM, specifically of quaternion algebra. Okay, let's try coefficients. So, what do we think is going to happen here? Because it's supposed to be a vector over the base parent ring, I think I should get a 1/16 vector, which is going to tell me a 1 in the 5th spot and 0s everywhere else. What? Oh, S is supposed to be a mat element. Over, yeah. Okay, that makes sense now. Some of these might actually be kind of fucked. S was supposed to be a matrix element. Okay, I gotta put some stuff back in there. But x dot coefs, it doesn't actually exist, huh? Access to undefined reference, get property. X dot has coefficients? False. Why is that needed? Yeah, every constructor seemingly for... So this must be something that you get after you... this must be a property that you get after you apply some functions to this thing. So what functions would we need to apply? How would I even see that? Like, I want to see functions that rely on this other function. Yeah. I don't think this is like, I don't know. Seemingly I don't see this anywhere, this coefficient thing. But if you call like basis on this, you call gens on this, you call basis on this, you call x dot. Yeah, weird. So let's put in some more information. Basis matrix. So I was right. Some ways. It's 16 by 1 instead of 1 by 16. But it did do this, and there was some hidden function that had to be called. And this is just so that there's a bunch of operations that you can do with these element types. Okay, so let's see. I'm getting a little bit hungry. I could make rice in the background. Which I think I might do.
There's something about him that makes a girl want to take him in her arms and...
Okay, so some things I essentially fucked up and need to go back and fix. For example, I'm not necessarily sure why. Oh, I'm not necessarily sure why matrix algebras are parameterized by two types. They're parameterized by a matrix element, and they're also parameterized by the coefficient ring of the base. So you know what we should do? Before going any further, kind of do want to write that, but before going any further, what we should do is we should go to Nemo, and we should find where in here it actually defines the matrix algebra element type, or matrix LM type. Could be an abstract algebra now. No. And just see how this works. So Nemo allows the creation of dense matrices over any computable ring R. There are two different kinds of implementations. A generic one for the case where no specific implementation exists. Provided by the abstract algebra package, and efficient implementations of matrices over a bunch of specific fields, usually provided by C or C++ libraries. So the following table shows each of the matrix types available in Nemo. The base ring R and the Julian-Nemo types for that kind of matrix. Okay. So if we have a generic ring, then this is provided by abstract algebra. The element type is going to be a generic matrix parameterized by T. And the parent type is a generic matrix space parameterized by T. So we should go to abstract algebra now. And check what this definition of the generic matrix space is. So abstract algebra provides matrix spaces, n by n matrices, and matrix algebras, which are n by n matrices over a ring. Both types of matrix provide matrix multiplication for matrices whose dimensions are compatible for multiplication. Only the latter of matrices forms a ring in the system. Matrix spaces provide a large number of linear algebra operations, including linear solving, elementary row operations, various canonical forms. The system also provides characteristic minimal polynomial computations, LU decomposition, determinant, matrix inverse, kernel computations. There's also code for computation of the Hermite and Smith normal forms over Euclidean domains, and Popov form for matrices over polynomial rings over a field. Most of this generic functionality is provided for arbitrary matrix types that satisfy the abstract algebra matrix interface. So kind of what we want to do is figure out at least Okay, so what we want to do is figure out still how does this interface work, and then really why is there one also in Hecke? Is Hecke's faster or is abstract algebra faster, for example? So we could continue reading in this. Matrix functionality, matrix spaces, matrix implementation. I'm also curious about this matrix interface.
guess I'd be too afraid to change something, because it could mess with the timeline that led to tonight.
Please. No. Oh, brother. I don't mind your dishonesty half as much as I mind your opinion of me.
How long have I been silent for? Fuck. I've been reading for like a while. Right? Okay. So, so there's also generic.dense matrix type. If you call dense matrix type on the type of an a type parameterized by a non-commutative ring element, then it should return the type of matrices with coefficients of type T, respectively of type LM of S. Implementations of the ring interface only need to provide a method for the argument of a subtype. The other variants are implemented by calling that method. Okay, so the generic matrix algebras is the thing that we're thinking about. Functions specific to generic matrix algebras of m by m matrices are implemented. Honestly, I kind of think that the reason why there's a matrix algebra type in Hecke now is because Hecke allows you to call matrices of non-commutative algebras. Matrix algebra represents a collection of all matrices with a given degree and base ring. In order to construct matrices in abstractalgebra.jl, one must construct the matrix algebra itself. This is accomplished with the following constructor, which allows you to construct the algebra of matrices with the given degree over the given base ring. Functions that do not return or accept square matrices or which cannot specify a parent include solve and null space. So if you try using null space on a matrix, I would assume that it would give you some collection of vectors. And then, yeah, you can't specify a parent from the outcome. Is that what the claim is? Sure. Okay. So, it throws a little bit of a wrench in things to the point where, like, what do we want to do with matrix algebra type in the central symbol algebras? Like, you should be able to call matrix algebra, and then we'll probably make just a split algebra type, and then make functions for something like this, right? Like, if you call matrix algebra tensor some arbitrary central symbol algebra, you just get Okay, I have to think about it. Because you could just get back a type exactly the same as in Hecke, a matrix algebra type, where there's a non-commutative ring inside the guy. I guess matrix algebras one. Okay, so the Hecke matrix algebra type really is for specifying specifically like R algebras where the coefficients are not the ring R. And I guess for abstract algebra, the matrices and the matrix algebras are matrix algebras of coefficients the base ring. Yeah. Yeah. So, okay, so I'm gonna have to think about it. I kind of don't think there's a good way to go about. I mean, I kind of think the best way to go about this is to have a split algebra type, which is going to mimic this matrix algebra type from abstract algebra. So apparently defined in probably here, but maybe the generic version. This might actually be it. So there's no struct here. Oh no, there is. The type is not here though. I gotta stop turning this shit off. So, what I was saying was we've got non-commutative rings, we've got abstract associative algebras, and then R-type abstract central symbol algebras lives inside of that. So I'm just right now essentially trying to figure out from matrix rings, how are we going to implement this or connect this with the central symbol algebra type? Obviously, a matrix algebra is a central symbol algebra. There's no question about that. I think that what we'll do, I'm not opposed to just having like a split algebra type. It's a little bit weird. And allowing for interaction between these two, yeah. Just trying to envision, like, if I have a matrix and I have a like an element in a quaternion algebra, should I be allowed to essentially like tensor the matrix with the element of the quaternion algebra to get some new element inside some abstract central symbol algebra? Is it worthwhile to say, for example, you have like quaternion algebra, matrix algebra, tensor them together, and you get matrix algebra over quaternion algebra? Or should it just be like a totally new abstract central symbol algebra, where you can no longer represent things by matrices? I think that's not ideal. I think that the default should be something like, if you have a matrix, you should always like try to be keeping track of the matrix as part of the algebra in some sense. Like, I think that like if there was a function to compute the index, for example, of a given algebra, which there will be in some cases, I think that when you call that, you should also be able to get a presentation. So like you started with an algebra, which was kind of arbitrary, then calling something like the exponent and finding out that the exponent's smaller than the degree or whatever should also somehow allow you to compute a smaller algebra in which the thing that you're looking at is a matrix ring over the smaller algebra. So and then if you have like matrix ring and a matrix ring over an algebra, you tensor those together, I guess you should just get like a bigger matrix algebra. That's kind of the default. I think that should be the default behavior, because that sounds kind of the nicest, although it's not the most straightforward to implement. So if I have two abstract central symbol algebras, I should be allowed to tensor them with a matrix ring and produce another matrix algebra over whatever the coefficient algebra was. I think that is the most reasonable thing. Yeah. Okay, then we're just going to take Hecke's implementation and copy it. But now we need to brainstorm kind of a new name. To some extent. Because I also think this is a confusing name, actually. Because matrix algebra element, you could make matrices the same way that abstract algebra does it. And that way, at least stuff like fast linear algebra maybe can be adopted. I guess it makes sense. I mean, it is like a matrix algebra. It's just a matrix algebra over some different coefficients. So in Asimai algebras recently, I've been saying something like, okay, I'm not perfect about this, but one of my collaborators told me that this is notation that him and his collaborators were using, and I thought it was pretty smart. So you call an Asimai algebra, you know, whatever. If it's not trivial Brouwer class, you call it neutral if it's trivial Brouwer class. And then you call it split if it's exactly a matrix algebra. And I almost want to call these like they're like known to be neutral if you have at least matrices of size greater than 1 by 1. Matrix algebra is not bad. Is there a name for this? Let's see. Strictly less than the degree. Is there a name for such algebras? It's just not a division algebra, yeah. Proper matrix algebra. Yeah, matrix algebra is actually pretty good. Pretty good name. Which means that we have to go through and look at so we have to go through and look at this comment, and I'm gonna do this when I get back. I'm gonna go make myself some lunch, I think. I put in a pull request, right? I mean, these are public, so I don't feel that bad sharing. I kind of also don't like just like pointing them out. They feel private to me. I gotta read this. All right, I'll let you watch this bird video. for a little bit. Plug this summertime birding lo-fi, since it's pretty good. And I'm gonna go make myself lunch, so I'll be right back. Amazingly, I'm back. I think that I'm gonna end the stream here to some extent. When I come back, I'm gonna come back later though, and I'm gonna do Nick's stream. So I still have a Nick's laptop that is not configured into a workable form, or at least a form that I like. So my goal is going to be to try to edit that. And just to summarize what we did today, we essentially went through and wrote down some types that we're going to add to this central simple algebra abstract type. Yeah, the big things eventually are to kind of make cross product and biquaternion algebras and some structure for them. I realized while doing this, because we didn't get very far, that basically my whole understanding of how the matrix algebra system worked in Hecke was kind of misunderstood. And the way that I wanted to redo this was just by defining kind of trivial algebras, which is, I think, not a good idea. So I think something like central simple matrix algebras would be better, although that sounds like a terrible name to me. So I have to brainstorm kind of what this concrete type should be. And then probably in the near future, what we're going to do is we're going to do something like, near future could be actually pretty far away, but we'll have two algebras. We'll define some way to combine them, like tensor product. And then maybe we can make some function like reduce, quote unquote, which will be able to take whatever algebra we have, do some things to it to figure out if it is a matrix algebra over some smaller algebra, and then present it in that form. So this type here should actually capture that somehow. So central simple structure constant algebras are going to be algebras that we can't really work with or are just given to us in an abstract way. And this split algebra type, I'm going to change this probably to something like matrix algebras or neutral algebras or something. And it's going to be kind of when we can take maybe an arbitrary algebra or some kind of structure algebra and reduce it to a matrix algebra over something smaller. So that's the goal, but I am going to end here and then come back later for Nicks. Nightly Nicks. Nicks at night. Something like that. Okay. See ya.